Okay, thank you. Yeah, so I guess the meeting is being recorded now. So last time we considered the homogeneous wave equation. Right? So that means homogeneous just means that these three terms are zero. Right? So, and this is what we did. We always first considered and with Dirichlet boundary conditions. And Neumann boundary conditions. I hope the spelling is correct. Okay, great. So this time we are going to consider this non-homogeneous PDE. This is the wave equation. So yeah. So if you think of it, I don't know if you are interested in such things. If you want to give some physical significance to this, then this means that there is a wave, and if I look at the endpoint of this wave, the position of the wave follows this path given by f1t, follows this rule f1t, right? If you think about it, right? And similarly, at this endpoint, the position is given by f2t. So at this endpoint, the position of the wave is given by f1t. Anyway, so let's just put aside the meaning of this equation in real life, and let's just see how to solve this. So as always, as in the previous case, our aim is to simplify these two conditions first, these two. And to do that, we make this substitution, z equal to uxt minus this thing. And clearly, z and u determine each other. Right? So solving for u is same as solving for z. But then, of course, z is going to satisfy a different differential equation. So here g of xt is going to be in terms of, it will be some function in terms of f, f1, f2. Right? And z satisfies these conditions. Z0t is 0, ZLT is 0. So these will be by construction, almost by our definition of z. And what is v of x going to be? So when we put z, let's just compute this since we have a lot of time. This is going to be ux0, which is f of x. And we are putting t equal to 0. So minus 1 minus x by L f1 of 0 minus x by L f2 of 0. Right? And similarly, we can find out w of x. Okay, so instead of solving this differential equation, we will simplify our life a bit by making this substitution, and then we will solve this differential equation. And the pattern to solve this is, you know the pattern, so let's just go ahead. So it is clear that we would have solved for u if and only if we have solved for z. So in view of this observation, let us try and solve the problem for z. So great. So by observing the boundary conditions, we guess that we should try and look for a solution of the type zxt is equal to znt times sine n pi x by l. So what do I mean by observing the boundary conditions? I'm referring to these two boundary conditions. These two conditions. Right? So from our experience so far, I mean, we guess that, okay, we should look for a solution of this, a series solution. We should look for a series solution of this type with the sign over here. Okay, so immediately what we are going to do is we are going to put this into our differential equation. So we differentiate this term by term. So we have z tt minus k square zxx. This should be equal to g of x comma t. But when we use this series solution, this term, and of course we assume that all our solutions are nice, so we can exchange the differential operator and the summation, etc. So this series just becomes this. So yeah, and we write g of xt is equal to summation n greater than or equal to 1 g and t sine n pi x by L. So this is the Fourier sine series of g of xt. So right, if you, and yeah, you can think of, we freeze t, so we get a function of x, and we write the Fourier sine series of that function, and the gnt is the nth Fourier coefficient of the value. Yeah, so the value of this function is the nth Fourier coefficient of gx with that frozen t. This is something which we have seen earlier, and I had explained this also last time. Yeah, so we want this equality, which means that g and t should be equal to this thing. Right? Yeah. So g x comma t is something which we know. In particular, we can compute this. We can compute this term g and t, this term, and our z is the unknown function. So our z and t, it satisfies this differential equation. Right. So great. So we have a differential equation which is satisfied by z, but we need more than that. We need two initial conditions to solve this differential equation. So how do we get those? We need that zx comma 0 is v of x and zt x comma 0 is w of x. So those are our conditions in the differential equation which we are setting, which we had set out to solve. So our zx should satisfy these two conditions also. So using these, we will get conditions on our capital Zn, right? So this thing zx comma t is equal to summation n greater than or equal to 1 zn t sine n pi x by L. And so zx0, which is equal to v of x, that's going to be equal to summation n greater than or equal to 1 zn0 sine n pi x by L. Now this is a known function, so we can find out its Fourier series. So I have used some notation, and that will tell us the values of zn0, right? And similarly, we have zt x comma 0 is going to be summation n greater than or equal to 1 zn dash t, 0 sine n pi x by L. Right, and this we want to be equal to w of x, once again, which is a function that we know, and so we can compute its Fourier sine series. So therefore, from this we will get the values of zn0 and zn prime 0, and we have this second order differential equation in one variable, so therefore the solution will be unique. Right, so the zn's are the unique solution to that differential equation, to this differential equation with these two boundary conditions. So thus we would have solved for zn's and therefore for our small zxt as a series, and therefore we would have solved the differential equation. Okay, so let's move ahead. Yeah. Okay. So this is an example. Yeah. Okay, so let's see if I can wade through this example. So let us now consider the following PDE. So this is our f of x comma t. And I've made my life easier over here. We don't have to do any substitution or anything because these two are already given to be 0. These two are already 0, so we don't need to make any substitution or anything. Let's go ahead. So from the boundary conditions, we are looking for a series solution for uxt. So we should look for, so we should look for some solution of the type ux comma t is equal to summation n greater than equal to 1 zn t sine by x by l. So L is equal to 1 over here. Okay. So, right. So if you remember, right. So what do we need? We need that utt minus uxx should be equal to e to the power t, and this is going to be equal to, if we assume that there is a solution, this is going to be right. So this is going to be zn prime prime t plus n square pi square, right? Zn t into sine n pi x n greater than equal to 1. So we want, and this thing we write as its Fourier series n pi x, and we want these two to be equal. Okay, so that's why I have computed here the Fourier sine series of f of this function e to the t. So notice that, this is just going to be the Fourier sine series of 1 multiplied with e to the t. So so this e to the t is just going to come out because, okay. So this is my f and t, the nth Fourier coefficient. So let's go to the next page. So the Fourier series is given by this. So this is the nth Fourier coefficient. Okay. Okay, I have done this computation also. The Fourier sine series for f of x is given by x into x minus 1 is this. This is something which we would have done earlier. Okay. So now we substitute this into the equation. So what we need is this term over here should be equal to this term over here, right? Let's just forget about this piece of information for a few seconds. Right, so let's see. So for n greater than equal to 1 and even, so if n is greater than equal to 1 and it's even, then this term becomes 0. This term becomes 0 if n is greater than equal to 1 and it is even. So therefore we get, this is the differential equation which is satisfied by u and t, which implies that u and t is some linear combination of cos n pi t and sin n pi t. Okay, but we also know what the initial conditions have to be. So the initial conditions, remember, they are going to be given by the Fourier coefficients of these two functions, right? So Zn0 is going to be the nth Fourier coefficient of this function, and Zn prime 0 is going to be the nth Fourier coefficient of this function, right? Let me just go to the previous slide so that, right? The Zn satisfied this differential equation, and Zn0 is the Fourier coefficient of this v of x, and Zn prime 0 is the Fourier coefficient of this w of x. Okay, so in our case, this w of x is 0, right? So, right, so what do we have? So if n is greater than equal to 1 and it is even, then we have this, and since n is even, the nth Fourier coefficient of f of x is 0. So we are looking at the nth Fourier coefficient of this thing. Right, this is our f of x. So since n is even, this nth Fourier coefficient is 0, and g of x is the function 0 anyway. It's a constant function 0. So its nth Fourier coefficient is also going to be 0 when n is even. So right, so therefore we get that unt has to be the 0 function. Right, this is just by uniqueness of the solution, because we have un 0 is 0 and un prime of 0 is 0. Okay, so for n greater than equal to 1 and even, we get that the UNs are 0. Right, okay. So let's see what happens in the odd case. For n greater than equal to 1 and odd, we get, so yeah, so once again, let's go back. This is our original equation. So now when n is odd, we are going to get 4 by n pi times e to the power t. So we have this is equal to 4 by n pi times e to the power t. That's a differential equation we get. And if we put okay, so I'm a little bit confused because here I have just substituted. Oh, okay. So here we have found out a solution of this differential equation. I see. Okay, right. So if you remember from your, I had forgotten this myself. Sorry about that. So if you remember from your differential equations course, when you want to solve an equation of this type, so this is, let's say, yeah. So you have to find one particular solution. So you have, let's say, you find some u and t, which solves this equation. Then you can add to this the general solution of this equation. Right, and the general solution of this equation looks like this. Okay, so we have to first find one solution of this. We have to find one solution of this equation, and the general solution of this differential equation looks like that one particular solution, plus we can take any general solution of this differential equation. So yeah, so we have found out one particular solution of this differential equation, and any other solution of this differential equation, this one, looks like we have taken this particular solution and we have to add the general solution to this, the general solution of this equal to 0. Okay, right, so every solution of this, so every solution of this differential equation is of this form. So any solution of this differential equation is of this form. Okay, so now we have to use the initial conditions to determine the constants Cn and Tn. So let's do that. So once again, we know what un0, and we are going to use un0 and un prime 0. So in the case n greater than or equal to 1 and odd, we have the Fourier coefficient of x into x minus 1 is minus 8 into n pi cube. Okay, so let's just go back once again. Yeah, so n is odd over here. So yeah, so that's going to be, that's right. Right, so this is going to be equal to, this should be un of 0. Right, so let's just check. So when I put t equal to 0, right, is this the term that we get? Right, that's correct. So when we put t equal to 0, we get this thing, and this we want equal to this Fourier coefficient. And on the other hand, when we take the derivative and we put t equal to 0, so then what do we get? So then we get the Fourier coefficient of g, but g is identically 0, therefore all its Fourier coefficients are 0. So let's just stare at the derivative for a second. So if we differentiate this and then put t equal to 0, so then we will get exactly, oh, okay, I think there should have been a pi over here, sorry. Right, a pi is missing. When I differentiate this with respect to t, I will get n pi dn cos n pi t. So I suppose a pi is missing over here. So using this, we can solve for dn and cn. And therefore, the solution we are looking for is this thing. Uxt is equal to, yeah. So all the n's are odd, so as we saw. So yeah. I hope this example is clear. I mean, it's very straightforward. Okay. But let me just pause for a few seconds in case anyone has any doubts. Okay, so let's move ahead. So let's look at the non-homogeneous wave equation, but this time now with Neumann boundary conditions. And once again, this is a standard template which we are going to follow. So we make this substitution. Zxt is equal to uxt minus this function. And then we are going to get this gxt is in terms of f1 and f2, right? And our z will satisfy this differential equation, these two conditions. So here we have a ux, right? Okay, and then once again, guessing by looking at these two conditions, we should look for a series solution in terms of a cosine series. So therefore we try for a solution like this, right? Okay, and what we need is we first solve this ztt minus k square zxx is equal to g of x comma t. So right, so what do we get? When we differentiate this series, we get this thing, and therefore we need these two to be equal, which means these two have to be equal. Right. So therefore, so which is that we need that the z's, which are the unknown functions for us, the gn's are known to us. So we need the z's to satisfy this differential equation. And to specify what z is, we need to know what these initial values are. And for that, we look at these conditions. Zx0 is equal to v of x, right? And zt x0 is equal to w of x, right? Maybe let me just write something over here. So zx comma 0 is going to be equal to summation n greater than equal to 1 zn 0 sine, I'm sorry, cos, right? Oh, this is going to be n greater than equal to 0 this time. Someone has unmuted their mic. I'd like to request them to mute themselves. Right, and we want this to be the Fourier cosine series for v of x. And similarly, when we look at zt x comma 0, this is going to be n greater than equal to 0, zn prime 0 cos n pi x by L. Right, and we want this to be the Fourier cosine series for w of x. Right, so that will give us the values of these in terms of the Fourier coefficients of wx, v of x, and w of x, which is exactly what I've written over here. And then this differential equation with these initial conditions has a unique solution, which is the solution that we are looking for. Okay, and then once we have solved for the zns, we look at the series solution, and this series is going to solve our differential equation for z, and therefore since z and u, they determine each other, we would have solved our original differential equation. Okay, great. So let me just pause here for a few seconds in case someone has any doubts. Okay, if there are no other doubts, so let's go ahead. So once again, we are taking the same example. So we have this, well, it's not same, but it's a little bit different. So here there's ux, right? So this is the Neumann boundary conditions. So both these functions are 0. So once again, our life is made easier. So we first find the Fourier cosine series of e to the power t. So once again, this is just the same as taking the Fourier cosine series of the function 1, because the e to the power t will just come out of the integral. Okay. And that is simply, yeah, because the Fourier cosine series for the function 1 is just 1, because 1 is one of the eigenfunctions, right? So therefore here we have to do nothing. So the Fourier series for e to the power t is simply e to the power t. Okay, great. And we also, okay, fine, this is something which we would have done earlier. We have computed the Fourier cosine series for this function. Let's just assume this. And we are looking for a series solution of this type. Right? So yeah, so we want this to happen. Which means for n equal to 0, we will get a differential equation. And for n greater than equal to 0, we will get this thing equal to 0. So let's just see. For n equal to 0, we get, okay, so when we put n equal to 0, so this term vanishes. So we get u naught double prime t is e to the t, and the general solution of this we know is this. Okay. So once again, we have what have we done? We have taken a particular solution of this. We have taken one solution of this differential equation, and then to that we have to add the general solution of this differential equation. Okay. So the upshot is that the general solution looks like this. And then we have to look at u0 of u0 and u0 prime of 0. And that will tell us the values of c and d. So let us now, okay. So in the case n equal to 0, we have the Fourier coefficient of x into x minus 1 is minus 1 by 6. So let's just check that. Right, so the first Fourier coefficient is minus 1 by 6. So we have u0 of 0 is equal to minus 1 by 6. That's equal to 1 plus t is 0, 1 plus d. Okay, which is exactly what we got here. And we also have u prime 0 of 0 is 0. That's because the second function that we took, this is 0. So all its Fourier coefficients are 0. So therefore, we have that u prime 0 of 0, u0 prime is equal to 0. So when we take the derivative, what do we get? We get e to the power u0 prime t is equal to e to the power t plus c. Right, so we get this condition. So using this, we solve for c and d, and therefore we get this. So this is a value of u0. Okay. So let's see what happens for n greater than equal to 1. So for n greater than equal to 1, as I remarked, for n greater than equal to 1, all the Fourier, so this function is actually equal to e to the power t times 1 plus 0 times cos pi by x, well, L is probably 1, plus 0 times cos 2 pi x by L, and so on. Right? So all the other Fourier coefficients are 0. So that's what, for n greater than equal to 1, these things have to be 0. Right? Thus the general solution is this. And now we have to find the cn's and dn's using the Fourier coefficients. So if n greater than equal to 1 is odd, we have that the Fourier coefficient, so let's just see. So when n is greater than equal to 1 and it is odd, let's see what the Fourier coefficient is going to be. When n is odd, the Fourier coefficient is 0. Right? So this coefficient is 0 when n is odd. So we get un0 is 0, and the derivative of the function is 0, and therefore the Fourier coefficient of that is also 0. So thus both un0 is 0 and un prime 0 is 0. So therefore both cn and dn have to be 0. When n is even, we have that the Fourier coefficient is this thing. So this is equal to un0 and un prime. Okay, so and un prime 0 is 0. Right, this has been the case in the previous example and this example also. Right. So from this, we get that dn is 0 and cn is this thing. So yeah, un, when we put 0 in this, we only get cn. Right. So thus when n is even, we get unt is equal to this thing. And therefore the solution we are looking for is this. So this is my u0. And this is for each n. Yeah, so here I have put 2n. So we only get the even n's. So this thing is our unt. So I hope this example is also clear to everyone. I mean, yeah, there is a very clever trick to solve these problems. But once we know that, then everything is quite algorithmic and we just have to follow that process. So this ends our discussion on the wave equation. So let me just pause for a few minutes, and finally we will say something about the Laplace equation also. So there also the discussion is very similar. So, but let me just pause for a few minutes, few minutes before we go on to Laplace equation. Okay, so since there are no questions, let me stop sharing and share a new PDF. Okay. Okay, so this is the Laplace equation. So this is the two-dimensional Laplace equation. So yeah, so this is a differential equation which we want to solve. So here we want to solve the Laplace equation in a rectangular region, right? So this is 0, this is A, and y is lying between 0 and B. I hope the presentation is visible to everyone. Can someone please confirm? Okay, thank you. Yeah, right. And so our u is a function in this region. It's a function in this region to the real numbers, and we want our u to be a twice differentiable function which satisfies this differential equation, right? And we are going to complicate our life even more. We are going to say that it satisfies these boundary conditions, right? So this is 0, this is A, this is B. So let's see. So in this example, we want u0 comma y to be 0. So the function should be 0 here. So let me mark this in a different color. The function should be 0 here. It should be 0 on this boundary. On x comma 0, here it should be f of x. And here it should be 0. Right. And it should be a nice function inside this region. Nice meaning it should be twice differentiable, and it should satisfy this differential equation. So great. So how do we do this? So once again, we will use our favorite method, which is method of separation of variables. So we apply the method of separation of variables. So, and we try to find some solutions of a smaller set of some solutions to a smaller set of conditions. So we let u of x comma y be equal to a of x times b of y, and then the differential equation becomes this, right? So let's see what is the right. So we will solve this differential equation along with these two conditions first. Okay, so then so we first assume, let's try to find some solutions of this type, some functions of this type which satisfy these three conditions, 1, 2, 3, right? So then this differential equation is this, which means we separate the variables, and which means each of these functions has to be a constant. And moreover, so when we look at this condition 2 and 3 over here, we get that u of 0y should be 0 and u of ay should be 0. And since we don't want b to be identically 0, this forces that a of 0 is 0 and a of a is 1. So this boundary condition on A forces that the constant above should be positive. And let us denote this positive constant by lambda square. So this is basically our eigenvalue problem. So have I not written? Yeah, okay. So this is the eigenvalue problem that we have to solve, right? And for each, so the only eigenvalues for which this has a solution is lambda n equal to n pi by a, and the eigenspaces are one dimensional, and the solution is given by this. A n x is equal to sine n pi x by a. Okay, this is something which we have seen many times now. This is the third set of example where we are seeing this. Okay. So what? Sorry. I'm sorry. What is y of b? This should be b of b. Okay. So, right. So now we go back to this condition. Right. Right. So, yeah. So already we have that. Okay. So the only values of lambda for which this thing has a solution is lambda n is equal to n pi by a. N pi by a. Right. And for each value of this lambda, we have this differential equation. This equation, yeah. So this equation is coming from what we saw earlier over here because of this. So this constant is going to be equal to lambda n square. Right? Okay. And now we also have, now we look at this condition 4. What does this condition 4 say? This condition 4 says that ux comma b is equal to 0. But this implies that a of x times b of b is equal to 0. So our, right. So therefore the problem we want to solve is, for b, is this thing, is this problem. This condition is there and this condition is there. But we put this additional condition, b of 0 is equal to 1. Okay. So what happens? So the solutions to the above equation are given by b and y is equal to sine hyperbolic. Yeah, so sine hyperbolic x is equal to e to the power x minus e to the power minus x by 2. Okay. All right. So therefore, for each n greater than or equal to 1, we get this solution. So this is my a n x, and this is my p n y. Okay, and then we will look for a series solution in terms of these. Right. And there's just one more condition which needs to be satisfied, which is that ux0 has to be equal to f of x. So let's see. So when we put ux comma 0, what do we get? Ux comma 0, that's equal to summation n greater than or equal to 1 alpha n sine n pi x by a, and y is equal to 0. So that's just going to be 1. Right? When we put y equal to 0, this whole thing becomes 1. So these alpha n's have to be the Fourier coefficients of f of x. Okay. Right. So let me just go to the theorem. So it says that if f of x is continuous and piecewise smooth on this interval 0a, so that f of 0 is equal to f of a is equal to 0, then we consider the Laplace equation with these boundary conditions. So then the solution is given by this formula. So the alpha n's are the Fourier coefficients of f of x. So I hope this is also clear. So this was a little, there was a slight, yeah. So over here, what we did was a little bit different from what we had done earlier, because we imposed this extra condition that b of 0 is 0. So to begin with, we only had these two conditions, this and this. Yeah. And then we impose this extra condition. But anyway, we have been able to solve our problem. Okay, so let's see. Okay, this is an example. It's going to be, yeah, easy as usual. So we have to solve this differential equation. So this is my f of x, and my life is going to be very easy because it's already given in terms of its Fourier sine series. So f is given by its Fourier series in the above example. Right? Yeah. So therefore, we can just write down the solution directly. Right. So this is, yeah, yeah, I suppose quite repetitive, and maybe now you guys are a little bit bored by it. But let's just look at the Neumann boundary conditions also. So once again, we will apply method of separation of variables, and here it's going to be a little bit different. Right? So we put u of, so first we will solve for these three, 1, 2, and 3. Right? Right. So we have, so let's see, where have I, yeah. So we will have to solve this differential equation. This is the eigenvalue problem we will be looking at. And this has solutions, yeah. The eigenvalues are lambda n pi by a, and for each eigenvalue there is, yeah, so the solution space is one dimensional. Right. So once we do this, then we look at this and we bring in this condition. For each lambda n, we have this is equal to lambda n square. Right. So this plus this fourth condition will tell us that b and b is 0, because we don't want, yeah, we don't want this to be identically 0. So therefore, yeah, and we will impose this additional condition b of 0 is 1. And the solution for this bn is then, yeah, b0 will be this and bn will be this. Okay, so let's just go ahead. Thus for each n greater than or equal to 0, we get this solution. And then we will look for a series solution. And when we put, now finally we will bring in the first condition, which is that u of x comma 0 is equal to f of x. Yeah, so I mean, okay, let me come to that question after I finish the discussion. So we consider this series, and so this will tell us that the alpha n's are going to be the Fourier coefficients of f. Okay. So therefore, okay. So let's just move to our final slide. So it says that if f is continuous and piecewise smooth on 0a, so then the Laplace equation has this solution. And once again, let's see a simple example. So here also the function is already given in terms of the Fourier cosine series. So our life will be very easy. Right. So we can just directly write the solution, which is this one. Okay. So after that, after this we have Laplace equation in polar coordinates. So here you will see Bessel functions in action, but I'm going to skip this part. This is not part of the exams, but if you want, you can look at it. So we had worked quite hard with Bessel functions, and we had said a lot of things about them. So if you want to see some of that in action, you can read this part. It's not very difficult. It's very similar. Once again, we will use separation of variables. And yeah. Okay, so now regarding this question, I don't completely understand why we are imposing b0 is equal to 1. Yeah, I suppose, I mean, we are just imposing the condition to simplify our life a little bit. I mean, the fact that the solution, we can find a solution even with this condition imposed is, yeah. Yeah, I don't have a better answer to that question right now. Are there any other questions? Right. If there are any other questions, people, I don't know, you can just unmute yourself maybe and ask. Although I prefer if people ask on chat, because I mean, I think when we have to write stuff, we have to think a little bit more and things become a little bit clearer for both for the speaker as well as for the person who is trying to answer the question. So I think the solution is going to be unique, but I'm not. Yeah, I think the solution is going to be, the solution is unique. So yeah, but I'm not sure about that. Yeah. Oh yeah, right. I mean, if B, let's see. Yeah, as far as just solving for one n is concerned, we can treat it as a normalization. But yeah. Yeah, possibly this, we can consider the solution as a normalization. That's a valid answer. Yeah, B of 0 can't be 0. Yeah.
Excuse me, sir.
Yeah. Who is
So
this?
Sagnik.
Okay.
Huh.
Sagnik, why? Okay, yeah, go ahead with your question. If I don't understand your question, then you will have to write on chat.
Okay, sir. Sure.
Yeah,
So
but go ahead. Let's give it a try.
it's more of a doubt that I had in PH 108. So what they
In
basically
PH
did there.
108, I'm sorry, I am no, I'm not going to answer any questions about PH 108. Or,
I mean,
or if,
they dealt with Laplace equation. I mean,
okay, so
electrostatics
what
and Laplace
happened?
equation.
Yeah. So what happened there?
There was a similar question like this rectangular thing, and you had
Okay.
zero voltage on all the three sides, but on the
Okay.
fourth side, you
Yeah.
instead of the function being continuous, you had like 10 volts. So the function
Okay.
was not continuous on the edges. But even after that, we were able to find a solution, and the
Right.
solution was continuous in the inner region minus this measure zero space, which is the boundary. So I was just
Okay.
wondering that
So that all that is
we
fine with us, no? It
uh,
fits in very well into what we did, right?
I mean, I had this confusion that we are adding continuous functions, but still we are somehow getting a function that is discontinuous on the boundary. So how
Yeah,
is
that's
it
because
possible?
why is it
Huh.
not possible? We are adding infinitely many functions. That's the point.
Yeah.
Yeah, if you add finitely many functions, there is no problem. You're right. If you add finitely many continuous functions and
Uh-huh.
you get something discontinuous, then you have done something seriously wrong.
Yeah.
Okay, but the point here is that you
Uh,
are adding infinitely many solutions, many continuous
so,
functions, and
so
then you
like
can get something horrible.
is the condition that f of 0 equals to 0 and f of a equals to 0 necessary for the derivation that we did right now?
I mean, we want something, we want this to happen, no? U of 0, when we combine these two,
Uh-huh.
you would want U of 0 comma 0 to be 0, right? Which is f of 0.
Uh-huh.
So I just put it because of that reason. Yeah.
Okay.
Yeah. Any other questions? So maybe on Thursday, I will come onto this meeting I will come to this meeting, and if people have questions, then we can have a discussion. Yeah, maybe we can on for Thursday's class, we can have like everyone can speak. So, and if no one turns up, let's say in 15 minutes, then I will assume that people don't have any questions, and then I will just sign out. So this is the plan for Thursday's lecture. And I suppose, yeah, I don't know if there are still questions on Monday, then yeah, we can decide on Thursday whether a class is required on Monday or not, next Monday. Are there any other questions? Okay, if people have questions, they can unmute themselves and ask. Okay, so if there are no questions, then let us end today's lecture. Thank you everyone for coming. So yeah, as far as the syllabus is concerned, I think I have covered all the material. And yeah, the NSEM is on 15th November. Today I sent a form. I'd like to request all of you to fill up that form if you haven't already filled it. Okay, thank you very much.